Hello guys, I'm Ali. I'm your online course instructor, and today I'm going to review a topic called central force motion. What are the learning objectives that I'm looking for? First, I want to show you how you can formulate a central force motion, and then I will show you how you can basically calculate the path of a particle which is under the influence of a central force. So first, let's define this type of motion. If a particle is moving only under the influence of a force having a line of action, which is always directed toward a fixed point, the motion is called central force motion. What are the examples? For example, the first one is electrostatic forces or gravitational forces, which probably as mechanical engineer we are more familiar with that. For example, satellites going around the Earth, or Earth is going around the Sun, or any other planet going around a star. So these are all central force motions. Now let's see how we can formulate such a problem. Let's assume that we have a particle called P with a mass of m, and basically we have a force acting toward the center, and I'm calling that F. And the particle is going through an arbitrary path. First of all, based on the Newton law, we know that if we consider a cylindrical coordinate, the summation of forces in the r direction toward the center is going to be equal to m, the mass, times ar, or the acceleration in the r direction. If we use the cylindrical coordinate, we can rewrite it as this, or minus f equals this equation. The same scenario for the theta direction. The summation of forces in the theta direction will be equal to ma theta, and again in cylindrical coordinate we can write it as this. The point here is it's a central motion, which means that we don't have any force in the theta direction. Therefore, the summation of forces in the theta direction will be 0. For the second equation, or the forces in the theta direction, which was 0, I can rewrite the equation like this. And if I integrate, it basically tells me that this part of the equation should be a constant, since the derivative of this term is 0, which means that this term should be a constant, and the constant I'm calling that h. The other topic that I want to talk about is areal area. Let's assume that the particle at point P, or the particle P, will move to point B. What is the area that it will sweep? If I assume it's a triangle, I can write down the dA, or the area, as basically half of one of the arms, or BP, which would be r d theta, and also r. If I multiply them together, half of that would be the area that the particle will sweep. And if we look at it and rewrite it, it's basically what we found before, and we said that it should be a constant in a central force motion. So basically the areal area should be constant, and in other words, the particle will sweep out equal segments of area per unit of time as it travels along the path. Now the other question is how I can obtain the path of motion, or basically find r as a function of theta. We found two different equations, an equation for force in the r direction and an equation through the force in the theta direction, which gives us a constant as h. And if we put these two together, and also we define a new variable as c equal to 1 over r, we can find that we have a basically partial differential equation which can define the path of motion. But to solve this equation, we need to have F, or the central force. For instance, for a gravitational force, or for a satellite going around the Earth, the gravitational force will be Gmem over r to power 2. G is the gravitational constant, ME is the mass of the Earth, and R is the distance between the center of the Earth and center of the satellite, and of course M should be the mass of the satellite. If we replace this F in the equation that we found, now we can find the path of motion. So let's do that here. If we do that and we solve the equation, I don't want to go through the solving process, we will find that the path of motion, or the equation for the path of the particle, can be written like this. And here I am showing an elliptical motion around the Earth for a satellite. But in this equation, I still have two things that I need to find out, or two parameters that I need to calculate. The first one is C, and the other one is H. To do that, I need to have some initial situations. The constants H and C are determined from the data obtained for the position and velocity of the satellite at the end of the power flight trajectory. What is the power flight trajectory? Basically the path that the satellite should go to reach to its orbit, and the moment that it reaches its orbit and will enter it, it's going to be a free flight trajectory. Basically, we need the initial condition for the free flight trajectory, or the end of the power flight trajectory. We call those R0 and V0. R0 is the initial height or distance to the space vehicle, and V0 will be basically its initial speed at the beginning of its free flight. So if we have these two parameters, we can find H and C. Now we basically have an equation to define the path of a particle under the influence of a central force. Now there is another parameter which is very important in these types of motions, which we call it eccentricity of the flight trajectory, and we will define that as E equals C h to the power 2 over g me, or the mass of the Earth. What is the advantage of this parameter, or E, or eccentricity? It basically helps us to figure out what is the type of the trajectory that, for example, a satellite is going around the Earth. Is it circular? Is it elliptical? Is it parabolic? Or it's hyperbolic? So in another word, so if E is equal to 0, the free flight trajectory will be a circle. If E is between 0 and 1, the trajectory will be an ellipse. If E is equal to 1, the trajectory is a parabola, which means that basically the satellite will never come back. And if E is bigger than 1, the trajectory will be hyperbola. Again, it will not come back. So for two of these situations, first, if E is equal 1, we can find out what is V0, or the initial velocity, which would be a square root of 2gme over r0. This will be for a case that the satellite follows a parabolic path, and it's basically on the border of never returning to its initial starting point. And this velocity is called escape velocity. We also have another situation where E is equal 0 and the path will be circular. The speed vc required to launch a satellite into a circular orbit can be calculated like this, which is a square root of gme over r0, provided that r0 represents a minimum height for launching in which frictional resistance from the atmosphere is neglected, or basically we are entering the free flight trajectory and there is no drag force. And the speeds at launch, which are less than this velocity, or vc, will cause the satellite to re-enter the Earth's atmosphere and either burn up or crash. And what about the elliptical orbit? All the trajectories attained by planets and most satellites are elliptical. For a satellite's orbit about the Earth, the minimum distance from the orbit to the center of the Earth is called RP here. And also I should mention that in this motion, the Earth is located at one of the foci of the ellipse, and also the maximum distance is called RA. And in this elliptical motion, the long axis is 2a, which will be the summation of RP and RA, and the smaller axis will be 2b, and it will be calculated as 2 times the square root of RPRA. But how I can calculate RP and RA? The minimum distance, or the perigee, will be equal to R0, and the maximum distance, or apogee, can be calculated using this equation. So now I can basically tell what is exactly this orbit, because I can calculate A and B, or the bigger axis of the elliptical motion and the smaller axis. In addition, the period of time required to make one orbital revolution can be calculated using this equation as well, and it can be useful for solving some problems. I guess I'm going to end this lesson here, and I will have another video in which I will put in use some of these equations. And I hope it was a useful lesson for you guys. Have a great day.